Introduction, and it's a great pleasure to be here for this workshop. So at first I intended to talk about spectral total variation, and then I looked at the program and I realized I would be the third person in the afternoon to talk about this topic, so I decided to change, and so I'll be talking about image and video colorization instead. This is some joint work with Fabien Pierre, who did his PhD on this topic, and also Aurélie Bugeau and Vinh Tong Ta. Here's the overview of my talk. I'll first present what I call the colorization problem, trying to introduce what this problem is to me. Then I'll present a first model, luminance coupled model. I'll try to say a few words about the algorithm to minimize the model we have proposed. And then I'll present two extensions, one where you add some user interaction, and a second extension for video colorization. So what is a color image? A color image, in fact, is the sum of two components. First component, which is the chromatic component, and the second one, which is a grayscale version of the color image, which is the achromatic component. And so what I call the colorization problem is given a grayscale image, I want to recover a possible color version of this image. Of course, it's an ill-posed problem, because it means that you have I will assume that the grayscale version of the image is your chromatic component, and I will try to find a chromatic component so that I can recover a plausible color image. And there can be many, given a grayscale image, of course, there can be many plausible color image that corresponds to it. So many plausible chromatic components. So I will just try to pick one plausible chromatic component to get a plausible color image. It's in some sense it's a weak version of the classical problem of image in painting. Okay. So I'll use the luminance component of the image. So the luminance component, for some reason, it's denoted by Y in the literature. So I don't know why luminance is Y, but that's the common definition. And it's a linear combination, so the coefficients may differ, but it's always a linear combination of the red, green, and blue components of the image. And why is this luminance component well used? It's because the human eye is very sensitive to the luminance component of the image. So basically, if you have only the luminance component of the image, you already have a lot of information on the image. And you can complete with the luminance component are associated the chrominance component, which I will denote by capital U and capital V. And you have a bijection from the classical RGB space to the YUV space. And well, basically what we assume that we are given a grayscale image, and that this grayscale image is the luminance component of the image, or the achromatic component, prefer. And we want to recover an associated color image. So there have been many works on this topic. I won't be exhaustive. But a first class of method is the manual colorization, where the user in fact puts some scribble on the image to colorize. So this type of method works well as long as there are not too much texture on the image, and as long as the user knows well how to place the scribbles on the image. But if you have a good user, you get very good colorization. Yes, once the scribbles are placed on the image, of course, it's just simple diffusion on the image to get the colorized version. And the second class of approach to colorize image is what I call the exemplar-based approach, where in that case you have what I call the target image, which is the grayscale image we want to colorize, And you assume that you have some source image, which contains, in fact, all the color you will need to colorize your image. And you will, in fact, you will use the color of the source image to colorize the target image to get a colorized version of your target image. So now the problem is, of course, to find a good source image when you have a grayscale image to colorize. So what is the basic of the approach? So you have your target image you want to colorize. You first, you choose a pixel in the image. You take a neighborhood. Here it's the square. And you want to find which pixel in the source image, in the grayscale version of the source image, has the closest neighborhood in some sense. So for instance, you may find this patch as the closest one to your patch. And then what you do with the exemplar-based approach is just that you take the color of the central pixel of the patch you've chosen, and you assign it to the image you want to colorize. So it's very simple, but in fact it's quite efficient. So here is an example of what colorization you can get with this type of result, where you have the target image in the middle you want to colorize, a source image you take the color from, and that is the kind of result you can get with exemplar-based colorization. So it's not perfect, but it's already something interesting. Something I won't talk much today, but which is a subject just in itself, is the choice of metric. In fact, how you compare the patch in the target image with the one in the source image. Of course, if you had a perfect metric to compare patches, the problem would be much easier. And for the moment, as far as I know, it's an open problem. So what we do is that we use several distances, several metrics. So here are the ones we have used, but you could use all the metrics you want. It's not meant to be the definitive list of metrics you should use. And so we use the standard deviation, the Fourier transform, and the cumulative histogram with different size of patches. And all in all, we will use 8 metrics, 8 different metrics. And then the game is to find which is a good metric for your pixel. So for instance, if you take a pixel here in this part of the image, you will get, depending on the metric, you will get different colors. Mainly you will get green colors, which is consistent because it's something which should be green in the image, I would say. But, well, if for some metric, you will take some blue or some white. And the question is how you choose the good one. Same problem. Well, if you take a pixel in the sky, you would expect to have something blue or light blue. But depending on the metric, you can get something green. And so you want to be able to choose the good metric, which gives you a good color. Of course, if you find the metric to compare patches, then this problem is solved. But we did not know how to do it otherwise. So how to fuse the candidate? There have been many approaches. I think the easiest one, or the first one maybe, is to use the median filtering. And then later, it has been proposed variational approaches or simulated annealing approaches. And so today, I will focus on variational approaches. But of course, it's not meant to be the only solution to fuse candidates. It's just a proposal which gives reasonable results. So I'll just say a few words about the functional which was proposed by Bugeau and Papadakis. So in this approach, so U, small u, is meant to be the chrominance vector to compute, so capital U and capital V. And W are meant to be weights to choose which color you will assign to U for at some location. So maybe I'll rephrase it. So the function is composed of a regularization term here. You want to minimize the total variation of U. You could use any regularization you want. It's just that this one works quite okay. Then this term is meant, in fact, if W is either 0 or 1, you just want U to be equal to one of the CI, to one of the candidates. So you want W to be equal to 1 if I is the good candidate, if Ci is the good candidate, and 0 otherwise. Of course, this is not a convex constraint to have W equal to 0 or 1, so you relax it and you just assume W to be between 0 and 1. And to force W to go to 0 or 1, you add this non-convex term here, and of course, which will force the W to go either to 0 or 1, classical 1. So you have also some constraint that the coordinates should live in some reasonable space, so that you stay in the RGB cube, and that the W should be all in between 0 and 1 and sum to 1, that you're in the simplex. So it gives interesting results. So the target image in the middle here to colorize with the source image on the left, and on the right, that is the result you can get with such an approach. So it still has some drawbacks, and well, we will see that we can do better, but this is what we will get in a few slides. Just the comparison is on the right. Much sharper, the color are much better, and it's also much sharper on the edges. Okay, so this is all just to introduce the problem, and now, if there are no questions, I'll go into the detail of the model we have proposed. So, as I mentioned earlier, we have decided to use a variational approach, but of course it's not the only solution. And we have chosen to use something which is inspired by the work of Bugeau and Papadakis, but which is different. So we take again the same, I would say, data term here, which is to force the U to be close to be equal to one of the candidates, Ci. So the W should be equal to 1 if you're at the right candidate, and 0 otherwise. We have changed the regularization. It's inspired by TV, but it's no longer exactly TV. I will speak about it later. And well, we still have the constraints for U and W, but we have removed, in fact, here this non-convex term on W, which was there to force W to go to 0 or 1. Because in fact we realized that it's not needed. In fact, what happened is that if you look just at this term, when you minimize with respect to W, if U is closer to one of the Ci, then the solution is trivial. You get the minimization with respect to W is just Wi equal 1 for the Ci, which is the closest to U, and 0 otherwise. So the W are binary weights for free. And in fact, that's what happens almost all the time. So there's no need to add this extra term just for a few pixels in the image that anyway you won't see. So the other main difference is the regularization. So that's not well, that's inspired by TV, but that's no longer TV. That's what we call the coupled total variation. So if the classical total variation on the chrominance component would be the one I've written, but with gamma equals 0 without the red terms. In fact, what we add is what we want is that the jump on the chrominance component should be located at the same should have the same location as the jump on the luminance component. And so this is the reason why we added this term here to force the jump of U and V to be at the same location as the one of Y. So it's very simple, but it works quite well. Just to illustrate the influence of this parameter, I get back to a very simple in painting problem. So I minimize here this functional with a coupled total variation, and M is just a masking operator. It's either 0 or 1. It's 1 when you know the color, while you have put some scribbles, and 0 otherwise. And you solve this problem. So if you use the classical total variation regularization, the jump and the chrominance component are not located at the same places as the one of the luminance component. And so you get something which is not right. With the coupling, well, then it's, of course it works. So it's very, very basic, but in the results, it has a real influence. Same kind of different experiments just to show the same thing. Here on this image we put two scribbles, and we saw what we get with the previous results, with the previous model, sorry, here in painting, with different values of gamma. So without coupling, of course, there's no relation between the jump on the chrominance component and the one of the luminance component. If we have put a strong coupling, then we recover exactly what we want, and with a coupling in between, well, we get close to the jump of the luminance component, but we are not exactly on the right location. So it's very basic, but it's very important for image colorization. And you can see it in when you colorize a true image, not just toy images. So for instance, here is the target image to colorize. On the right is the source image we use to colorize. And if we look at the zoom in here, it's this part of the image. If you look at the edge between the mountain and the sky, you see that without the coupling, these two results on the left, you have some transition, whereas with our model, with the coupling, it's almost a perfect edge. So this may look as trivial, but this makes really a change in the colorization. So some further examples, just to compare with some with other methods. So on the second column are the target image to colorize. On the first column are the source image we have used to take the color. The third image presents the results we get, and then the fourth column is the results we get with the algorithm of Gupta, and the last column is the results we get with the algorithm of Welsh. So I don't claim that our result is better, just claim that we get something which is plausible and which compares well with the other approaches. There's no way to say it's better just on these examples, but it seems to be working. So further example with our approach. So in the middle are the target image to colorize. On the left, the source image with a view to take the color, and on the right, the results we get. So I think it's quite reasonable. Other examples are here, and so you always have the image to colorize in the middle, the source image on the left, and the results on the right. So the first line is it's an image of March planet. So nobody's been here, so you can put the color you want, as long as it looks plausible. Second line, it's a picture from the town of Guérande in Bretagne. So it's an old picture, and you can restore it with using a recent color picture and get something like that. And the last line, that's the Taj Mahal. So I don't remember if this one is the left entrance and this one the right, well, the south entrance and this was the north entrance, or the contrary, but it's not the same building on the two images. We use one another to colorize. Okay. So just to write a few equations, I'll say a word on how we compute the colorization. So to be quick, I'll use well, we are going to use a primal-dual approach, and a basic operator, a basic tool in this setting is the proximal operator, which I assume all of you know, which the argmin of this quantity here. Okay, so what we have is a non-convex model. So here the functional we have introduced. The non-convexity, in fact, comes from this term here with the coupling between W and U. You have a product which is non-convex. So if you can rewrite in a more formal way your functional this way with F, G, and capital H convex functions. But here you have a coupling, small h, which is convex with respect to each of its variables, but which is not globally convex with respect to both variables. So if h was convex, then we could apply, for instance, the algorithm by Antonin Chambol and Thomas Pock, and everything would be fine. But since it's not convex, it's a little more it's more complicated. Well, we have tried hard to get a converging algorithm, but well, somehow we have a converging algorithm, but not a fast one. So to get a to get a converging algorithm, we can use in fact the Palm algorithm, which was introduced by Boll, Sabar, and Teboul in 2014. Well, they are interested in this functional where f and g are convex functions, and h is the smooth, possibly non-convex function. So it's of course our functional is in this setting, even though we are a little more regular, and we can apply their algorithm. So what they have shown is that provided the functional satisfy the Kurdyka-Lojasevic conditions, then you can compute a local minimizer with the algorithm, which is some kind of generalization of the forward.call algorithm. Well, basically, you just iterate a proximal operator of the function f and g. And the problem in our case, so we can do this, but the problem in our case is that the function f is small f is this function capital F with the operator capital K. And so the proximal operator, in fact, in this case, for the total variation, we have to compute it with an iterative algorithm. So it leads us to use an algorithm with inner loops, and which in practice is quite slow. So if you want to have guarantee of convergence, you should use this algorithm. But what we have decided to use is a different strategy. We have decided to use a primal-dual approach. Even though, well, unfortunately, we were not able to prove the convergence of the algorithm. It gives similar results, and it is much faster. So, and just a remark is that, in fact, if it can be seen as a particular instance of the Palm algorithm if you just do one iteration in the inner loop. So, somehow, our algorithm can be considered as an approximation of the Palm algorithm. It's not a proof of convergence, but at least, well, we can relate it to some converging algorithm. The problem here with the saddle point problem, the saddle point computation, is that since it's non-convex, we are not able to prove that indeed a saddle point exists. So, and contrary to forward-backward-like algorithm or the extension by Teboul and co-authors, we have no criterion to minimize with this approach. So we don't know yet how to handle this problem with the primal-dual approach with in the non-convex setting. Okay. So now I'll speak about two extensions of the model. One where the user can also add some information. So if I get back to the results we got for image colorization, for instance, with the Taj Mahal image, if you look at the result we get, we have some, for instance, that the water is brown, the trees also are brown here, and well, I don't know, I've not been here, but I would expect the water to be blue. Maybe it's brown, I don't know. And I would expect also the trees to be green. It's just a guess, but I would say a reasonable guess. And so the question is how, once you get this result with the algorithm, how you change the color in an easy way so that you get something you like better. So what we have decided to do is, in fact, to add some candidates, some possible candidates, and for that we will make use of the non-convexity of the functional. So the basic idea is that we will allow the user to put a scribble on the image, but we don't want the user to put many scribbles. We just want him to put few scribbles in the image to help get a better colorization result. So for instance, here we put a scribble in the sky, and we computed some geodesic distance to the scribble. So that in fact for the blue candidate, the distance will be 0 all over in the sky, and will be infinity almost everywhere else. just based on the gradient, just a geodesic distance to the scribble. And so you did. So you add this candidate to the list of candidates you had with the previous algorithm. It's just that you get from 8 candidates to 9 candidates. And here the result you can get, for instance, so the image to colorize is this one, the target image. This is the source image, you take the color. So if you don't interact, that is the result you get. If you just put one scribble in the sky, here the blue one, you will recover a blue sky, contrary to the original result, but you will get some blue in the bottom of the image. So you have also to add another scribble on the track here, and then a third one in the middle to get something which is, I would say, almost perfect. So the idea that the user can interact so that you can improve the first result, get the second result, and then the third result to get something you want. But you don't have to put scribbles all over the image. It's not like the manual approach. It's just a few scribbles to get something better. Another example with the target image of a rose to colorize, and the source image we've used. So that's the result we get without any scribbles. But if you put some red scribble on the rose, and we get a red rose. If you put some purple scribble, you get a purple rose, and blue scribble, you get a blue rose. We have to put more scribbles the further the color we want to add, the more scribbles we have to put on the image. For instance, red is quite consistent, so just three scribbles are enough. But for blue, we have to put much more. So if I'm back to the example of the Taj Mahal, we can add the water blue and the trees green just by adding scribbles here in the tree, and the blue is purple. So here there are 3 scribbles, 2 in the trees and 1 in the pool. Just to modify the first image we got, to get something which I would say I prefer, but then it's just a matter of taste. Okay, so we can play the same game on other images. With the grayscale image to colorize, the source image we use to take the color. That's the results. On the left is the result we get without adding any scribbles. And on the right is the result we get by adding a few scribbles. So we have the background, which is not brown as in the original image. I think it's better. Another example. Here, it's an image of the funeral of Victor Hugo. So none of you was there. But we took a recent picture of Arc de Triomphe, and we used the color of Arc de Triomphe to colorize the funeral of Victor Hugo. And this is the result we get without user interaction. And if we add a few scribbles, for instance here you see we have to add some green, but also we have to add some brown. Whoops, we get this type of result. As an example, Michel Morgan. So just to show how it works, there's a MATLAB code you can download on the web. So you just load an image you want to colorize. For instance, okay, you can take Michel Morgan. Then you load an image you want to take the color from. I won't take any image, but a reasonable one. So now it computes the candidates, just the basic exemplar-based approach, and you get the result in the middle. Of course, you may want to improve the result, so you may add some scribble, for instance, in the sky. Okay. Not wasn't that much. For some reason. Okay. Well, okay, that's not. I don't know why it does not want me to put another scribble, but that's not bad. I'll just minimize the functional with one scribble. So half of the. Okay, well, I'll try again later, but for some reason.
So the mouse is not red.
Yeah, I can. I should add some red, but I'll try to start to quit Windows and no, to quit MATLAB and start it again. Okay, I don't know. Now it works. So I can put some scribble in the sky. And I can also put some scribble on our lips if you want. And then I can minimize the function. No. So you get red lips. Of course, you can well, you can get better results if you put more scribbles. And you can play. You can do whatever you want. It's very easy, and I don't know why it failed.
The eyes, you would expect it to be able to generalize from this one that the eyes are white and
you put some white in the eyes.
No. Then you are doing everything by yourself.
Yeah, well.
It's a fantastic algorithm. It makes the user work.
Exactly.
It's called what's it called? It's called the crowdsourcing algorithm. And the crowd is one.
Okay, so well, we can play with it later.
Mm-hmm.
Okay, so I'll finish with an extension to video colorization. How much time do I have?
About 10 minutes.
Okay, should be okay. So why is it interesting to colorize videos? For instance, there was the Apocalypse series, which was broadcasted in France in 2014. It was in fact movies taken during the First World War, but of course black and white movies, and so that the people who would be interested, and especially a young audience would be interested, they colorized these movies, and it was quite a success because many young viewers watch it. And so there were 4 hours of video to colorize, and it was manually colorized, and it took almost a year to colorize. So there's a real need for automatic tools, or at least semi-automatic tools, to colorize video. Of course, since we had an algorithm to colorize images, we have tried to adapt it to colorize videos. So here's the overview of the approach. First, we look at the grayscale video. So for instance, we have the frame at time t-1 and at time t. And we want to compute some correspondence map between these two frames. In fact, we want to guess, for instance, for a pixel here, if its color comes from a pixel in the sky or its color comes from a pixel from the person here on the left of the image. So this will be the candidate's choice that we did with the exemplar-based strategy for the still image. Here it will be based on these correspondence maps that will be, well, I will explain in the next slide how I compute them between the two consecutive frames. How does this pixel come from the sky or from a guy or from other part of the image? And so which color should he have? And then once we have computed these correspondence maps, we assume that we have colorized the frame at time t-1, and we want to colorize it at time t. And so we just decide which is the good correspondence map, and we take the color, for instance here, in this case, of the pixel of the sky, to colorize the sky in the frame at time t. One of the motivation of the approach was to get something interactive. That is, we wanted to be able to, if there is some error, to be able to stop the algorithm at once and not to have to compute the whole 3D plus t, the whole 2D plus t block, and then look at the result to see if there's a problem and then reprocess it. So that's the reason why we assume that we have colorized the frame at time t-1 before we colorize the frame at time t. It's not a global strategy, it's a local strategy, but to be more interactive. So just to illustrate the fact that depending on the choice of the correspondence map, we can, for instance, here the pixel on the table, it could come from, since there is some blue, it could come from these blue things, or it could come from the table. So we have decided, many correspondence maps could have been chosen. We have decided to use two maps, one which is based on the TVL1 optical flow, which works well for rigid objects, and the other one which is just based on the patch match algorithm, which works well for texture part in the image. And then we just want to, of course, to choose all the time the right correspondence map. And for instance, here that's the color we get. If you just use the correspondence given by patch match, so you get some green on the table, which should not be here. Or that's the colorization you get with the TVL1 optical flow. So there is some problem here close to the moving object because of it has I don't know, but it left something on the table. And if you combine both, then you can get something which is almost perfect. So just to fix notations, there will be the correspondence candidate C1, which come from the patch match algorithm, and the correspondence map V1 associated to it, and C2 and V2 will be for the TVL1 optical flow. Okay, now if we look at the model, of course it's inspired by the one for still images. So we have the same data term. So the only difference for the data term is that we only have two candidates and not more. But we could have more, of course. So it's just in our case we limited ourselves to two candidates, to two correspondent maps candidates. We still have the regularization on the chrominance component. We have some constraint on the chrominance component and the weight W, and we also had to add some regularization on the vector field, on the correspondence map. VT, without this regularization, the correspondence map was too regular. We already had to add this term to get something consistent. We don't want the color to be taken from two different parts of the image. Okay. So I will skip this part. It's just we use again a primal-dual strategy to get an algorithm which works, which is not too greedy in time. And I'll just go to explain what happens when there's a problem. So, for instance, the colorization may be wrong at some point. Here, it's due to an occlusion. You have a false color which has appeared between the right of the boy and his leg. So how do you correct it? You stop the algorithm. You add the scribble with the correct color at the location where there's the problem. You propagate the scribble with the coarse approach, just a geodesic distance, and then you minimize the correction model, which is given on the next slide. So it's just again you have the data term with this new candidate. So you have, that's why there's the tilde. You have the constraint, and for the regularization, here we regularize the chrominance component on the whole 3D cube, but just a local 3D cube, in fact. We just take a few frames to correct it. So here's the workflow of the algorithm. You have the initial frame. You assume that you could colorize it. Then you make the frame-to-frame propagation. Of course, you control the quality. Some user controls the quality, and if he detects some error, he stops the algorithm. He adds some scribble. He applies the correction model, and then we are back to the frame-to-frame propagation. So the interest of the approach is that we can stop the propagation and correct at once the result without having to perform to colorize the complete 3D cube, which is the case in most of the existing methods. So that's the main advantage of our approach, this correction possibility. So here's an example of a Charlie Chaplin video. So on the first two lines, it's with the Yatsiv and Sapir algorithm. So you can see that they have to put a lot of scribbles on the frame to get something which is nice, whereas here, in our case, well, we need the first frame to be colorized, but then it works without correction in this case. And there's an example taken from Nemo. Also, I think it's, but the quality of the result is quite similar, except that we need much less scribble. And for instance, if you look at the tail of Nemo, I think it's slightly better with our approach than with their approach, where there is some blue in the tail, whereas it's more red in our case. Okay, so just other example to show that we get something similar but with much less scribble. Well, just to show you what it does when it's a video. So it's Général de Gaulle. So there is a problem here. If you look at this thumb, it gets blue when it's occluded. So you can correct it with by adding a scribble, but in this video we did not do it. Another example with Pied Nickelé. It works quite well. Of course, there's a problem here. For instance, since there is no edge, it can no longer assign the correct green color. It takes the color of the sky. So it works quite well, but the model has its limitation, and you can see the limitation of the model in the results. Maybe. Okay, so the Charlie Chaplin result. Maybe it's better this one. So that's the boy sequence. I don't know why. No, it doesn't. Okay, maybe no. Anyway, so if you look here, you see that there is the problem I mentioned earlier, that a false color has appeared. So if you put a correct scribble at this location, then you will get the problem has disappeared. But the ground is as the correct color. So you really can interact with the algorithm and get nice results. Another example, I think it's General de Gaulle and Jackie Kennedy. So again, it's well, there are some drawbacks, but it's still quite okay. Okay, I will end here. So do not hesitate to download the code on Fabien Pierre webpage, so you can play with it, and feel free to ask your questions. Yes, Mila?
I have a first question, which is, you in the beginning you started with the luminance model.
Yes.
Why? When you take an old gray value picture, how can you know if this is the luminance channel or something to the intensity channel?
It's an assumption of the model. We assume that it's the luminance of the image, but it's of course there's no reason why it should be the luminance of the original image. It's just that a plausible way to color an image is to assume that the grayscale version you have is the luminance component. But we have no way to know what is the original luminance component of the image.
One way would be to change a little bit the histogram of the input gray value image so that it resembles more a luminance channel.
Okay, in the case when you can take a picture, a new picture of the same scene, yes. But maybe we can talk about it later. Yes.
So at the beginning, you get rid of the box constraints on the weight, this
Yeah.
WI, right? So I wonder if that's a property or it happens every time that you can do that, or
Okay, so I do not exactly. What I did is not exactly. I keep the bound constraints. It's this little different. Oops. Okay, where is the model? Here, I still impose the weight to be in the simplex, so I still impose the weight to be between 0 and 1 and to sum to 1. What I removed is just this non-convex term here, which was meant to force W to go to 0 or 1 at convergence.
and without that term you get like
Yeah, in fact, what happened is that if you look at the functional here, if you assume that okay, if you minimize it just with respect to W, you forget the minimization with respect to U is fixed. Okay, you look at the CI, which is the closest to U. Then for this guy, WI should be equal to 1. That's the one which will minimize your functional. And WI should be WJ should be equal to 0 for all the other values. You won't be able to get a lower value for your data term. So if you just look at the minimization problem with one variable, you see that you don't need the extra term. Of course, it's just a heuristic explanation, because when you get to the joint minimization, it does not work any longer. But in practice, then what we have checked that for almost every pixel, we did not need this extra term, and it's much faster without it. And from just the human eye point of view, we don't need it.
What forces with this function, or what forces the things to change in the same location?
It's what I call the couple total variation here. That's this guy here. Because in fact, what I update are only the chrominance components. The luminance is fixed. So I only update capital U and capital V. Y does not change. But by adding this term here inside the integral, I force it's cheaper for the algorithm to put the jump of U at V and V at the location of the one at Y than at other places.
Why?
Well, I cannot prove it in general, but on simple on toy example, I can prove that you get a lower energy if you put the jump of u at the same location of the chrominance component.
That's very interesting. You know why I'm asking? Because we worked very hard to make things change in unison. You know, it's not. It was something that was very crucial for us. So if you have another magical wand, I'm really interested in it.
Well, it's a very, very basic one. It's almost trivial, but it's
but
in our case it works.
Do you see? I mean, I don't see why these functional forces things to happen at the same location.
What?
You?
It's strictly subadditive if you write it well. So I think it.
I see. So
it's better to prove.
that you have to
I mean, I
teach
don't know
me.
for this particular
You have to
section,
teach
but I
me
think
this
that's-
because because we had to use this sparsity and the joint sparsity in order to achieve the same result.
But yeah.
Mix now, I think there are plenty of presents of this.
Excuse me?
About mix now.
Yeah.
This is quite stable, I think.
Okay, so tell me about it. Okay.
Yeah.
Good. Okay.
It's very simple. It has not complicated the novel.
No, but the results were very impressive with this, and I want to understand the mechanism.
Okay, in the paper I show a very simple toy example where you understand why the jump should be at the right location. So maybe we can look at the paper together after the talk.
I think we should finish. So I would have two questions. One here.
So if I get this correctly, like in this coupled TD term, I think that you actually prefer solutions which have a similar jump height, like in U and V, because like you have this gamma in front of the luminance channel,
Yeah.
but then you somehow put the same weight to U and V, and I think there are coupled TD terms where you can actually enforce edges to be at the same position without having this additional idea behind. So I don't know how.
Well, with I'm not sure I understand well your question. The other nice way of doing it is the work by Martin, but it's somehow it's not exactly the same kind of term where you can impose the jump to be at the same location. I'm not sure I understood correctly your question.
Yeah, I think like you can enforce the jump to be at the same position between those channels somehow.
Yes.
Without the additional assumption that the jump height should actually be similar. Like here, I think you would prefer something where U and V have a similar height in the jump, so the magnitude.
I'm not sure that the height of the jump should be similar. But there's no reason why they should be. But maybe there is. I don't. Then you have to explain it to me. I don't know.
And maybe we can.
Yeah.
You had a question?
Yeah,
should
or
finish, so
maybe-
very short.
Yeah, it's also a comment like points on that. There's also something if you take like the norm of the Jacobian, like that has like dx, dy. Because we've used that, for example, for flow images, and that works really nicely. And actually tends to put the jumps in sync.
Or
So
spectral nodes.
Yeah,
There are
yeah.
many
Or
similar.
or Schatten norm.
But it is strictly subadditive. So,
Okay.
I think we should thank.
Thank
And then
you.
we can do